Okay, let's try to understand quantum wave function. So, mm, we know that electrons they behave like a wave, but the question is how can we picture an electron, a microscopic particle traveling as a wave? Um, Scientists were also battling with that question, so they wanted to formulate or come up with a mathematical description about how the electron behaves as wave, or a mathematical description about the shape of the wave, that is wave function. So the wave function is given by psi of x. This is called the psi. Now, and the second objective was to interpretation of this wave function psi. Then came one scientist called Schrödinger, Erwin Schrödinger. He gave us the wave function, negative h cross over twice m. So here, this is the Schrödinger wave equation, and here we have a bunch of partial derivatives, and we have the reduced Planck constant. But the important thing is that in this equation we have the wave function psi, and if you solve this equation and plot it, then we get something like this, and so on. Now, Schrödinger couldn't even explain what this psi is. He after solving the equation, we get a plot of the graph, but he couldn't explain what was this all about, because the explanation he gave was that electrons were like uh, electrons were distributed throughout an atom, like for water has to be distributed for water waves, then we can see the water waves. Similarly, electrons was he thought like a distribution of charges, and then the wave, uh, and it travels like wave, that the water waves, but it was wrong. Then came Max Born. Max Born. He he interpreted this wave function psi as that if you square the wave function, then you get the probability density. Probability density. That means once you square a wave function, it's like these are these are the these are the areas where you'll be able to find the electron, or where the density of the electron is maximum. These are the functions where you'll get the maximum probability. But which means that in any measurement of quantum, you have to measure it over and over again. Suppose at one time you'll get a particle here, sometimes here, here, and so on. So if you repeat the experiment, then you may find most of the time that electron will be residing here, or here, or here. But these are the areas where the probability of finding the electron is 0. These are the places, these are the areas where the probability of finding the electron is 0. That was how Max Born interpreted the function psi. So let's move on to quantum numbers. Now, in Bohr's model of atom, we know that the electron is outside of the nucleus in fixed orbit. Electrons are in orbits. But from quantum mechanical point of view, quantum mechanics, the electrons are in orbitals. That is the difference. So we can describe the orbitals using the 4 quantum numbers. There are 4 quantum numbers, and by using those 4 quantum numbers we can describe the orbitals. Now the first is our principal quantum number. Principal quantum number, and it is denoted by the letter n, and this n can have integers, starting from 1, 2, 3, and so on. Now this principal quantum number describes the mean energy level, or sometimes we call it as the shells. The shell. You can think it of this way, that the first energy level when n is equal to 1, suppose this is n equals 1. So when n is equal to 2, the electrons will be farther away from the nucleus. When n is equal to 2. That is how you can picture the principal quantum numbers. Next up is our angular quantum number. Angular quantum number, or sometimes we call the azimuthal quantum number, and it is denoted by the letter L, and L can have values starting from 0, 1, 2, and so on till n minus 1. It will have values 1 less than the principal quantum number, and this angular quantum number describes the shape of the orbital. So when n is equal to 1, then L will have, and since it is n minus 1, L will have 1 minus 1 will be 0. And when n is equal to 1 and L is equal to 0, then it is describing the s orbital. The s orbital, and it is spherical in shape. And when n is equal to 2, then L can have values 0, and n minus 1 will be 1. So when L is equal to 1, it is describing the p orbital, and the p orbital has a dumbbell shape, shaped as a dumbbell. That means in s orbital, the electron distribution is, you can find the electron, the maximum probability of finding the electron will be in this space, And in p orbital, in this sphere, I mean in s orbital, and in p orbital, the electrons will be found at these two sides, the two sides of the dumbbell. And these are also called as the subshells. Next up is our magnetic quantum number. Magnetic quantum number, and it is denoted by m sub l. And m sub l can have values ranging from negative L to positive L. So, and this describes the orientation of the orbitals. So, when L is equal to 0, then ML, the magnetic quantum number, will also be 0. And suppose the orientation is like, if you think of the Cartesian coordinates, and we know that when L is equal to 0, it's the s orbital and it's spherical, so it won't have any direction. It will have no direction in the Cartesian coordinate, the 3 dimensions. It will be same everywhere. Therefore, the magnetic quantum number is 0. It doesn't have any specified direction. But when L is equal to 1, then ML will have values ranging from negative L to positive L. That means negative 1, 0, and plus 1. So if we think in terms of the Cartesian coordinate, suppose we label these as x, y, and z. So for negative L, the p orbital will be oriented towards the x-axis. So we'll call that as the px. And in another case, x, y, and z. So in another case, it will be oriented towards the y-axis. And on the other case, the final case, x, y, and z, it will be oriented towards the z-axis. That's how there will be 3 orientations for the value of L equals 1. Now the last quantum number is our spin quantum number. So it is denoted by m sub s, and it can have values plus half or minus half. Now, what is this spin quantum number? So the analogy is like, suppose an electron it can rotate this way or the other way. So but actually in reality it's not spinning. If we but to picture it, that it can rotate anti-clockwise or clockwise, we can picture that way, but in reality it's not. So when it is rotating this way, we can denote it as plus half or up spin, and we denote with this arrow up. And when ms has a negative value, negative half, 1/2, then we'll call it as the down spin, or an arrow pointing downwards, the down spin, up spin, and down spin. So to generalize, let's make a table of the principal quantum number, the orbitals associated with it, and the number of electrons in each orbital, and number of electrons in each shell, or the main energy level. Now the number of orbitals are given by the formula n squared, and the number of electrons in the main shell or the principal shell main energy level is given by twice n squared. So when n is equal to 1, we know that L can have values 0 and our magnetic quantum number will be 0, 2. So it's describing the s orbital, and it's just the value is 1. 1 squared is 1. And the number of electrons, maximum number of, let's put maximum number of electrons in orbital, it can hold a maximum of 2 electrons. And so for when n is equal to 1, the number of electrons in each shell, in this particular shell, will be 2. That means 2 into 1 squared will be 2. And when n is equal to 2, L can have values 0, L can have values 1, and our ML values will be -1, 0, and +1. So when L is equal to 2, it's describing about the s orbital, and when when L is equal to 1, it's describing about the p orbital, and the p orbital can have have 3 subshells. So number of electrons in each orbital is 2, and here we have 3 orbitals, so each orbital carries 2 electrons, so 2 into 3 it can carry a maximum of 6 electrons. And the number of electrons in the shell, in this shell, when n is equal to 2, so twice n squared, 2 into 2 squared, will give us 8. So it will have 8 electrons. When n is equal to 3, L will have 0, L can have 1, and n minus 1. L will have a maximum value up to n minus 1, so n minus 1 will be 2. So when L is equal to 2, ML will have -2, -1, 0, +1, and +2. So this is describing about our s orbital. When L is equal to 1, it's p orbital. When L is equal to 2, it's d orbital. So d have 5 subshells. So 2 electrons, 6 electrons, and 2 into 5 is 10 electrons. So the shell will have twice n squared. That means 2 into 3 squared will give us how much? 9 to 18. So we'll have 18 electrons. So when n is equal to 4, L can have 0, 1, 2, and n minus 1 maximum is 3. So when L is equal to 3, ML values will range from -3, -2, -1, 0, +1, +2, and +3. So electrons 2, 6, 10, and here, since it's describing about the f orbital, and it will have 7 subshells, so 7 into 2 will be 14 electrons. So if you put in this twice n squared, so 4 squared is 16, and 2 will be 32. So it will have 32 electrons in the shell. So let's talk something on Aufbau's rule. And Aufbau is a German word meaning building up. So the electrons are filled in the increasing order of their energy, or simply put, in the electrons are filled according to their principal quantum numbers. Now suppose if we think about an atom, let's say a noble gas, argon, helium, neon, let's say neon. So neon has 10 electrons. So the first 2 electrons will go in the 1s orbital, then the next 2 electrons will go in the 2s orbitals, and the remaining electrons will go in the 2p orbitals. So that completes the 10 electrons. Suppose 1s, the s orbital can hold a maximum of 2 electrons, 2s can hold a maximum of 2 electrons, 4, so we have to reach 10, so 2p 6, and p orbital can hold a maximum of 6 electrons. So that is how we write the electronic configuration. Now when we talk about, suppose say calcium, so calcium has an electronic configuration. Okay, before going to calcium, let's talk about sodium. Sodium has 11 electrons, so 1s2, 2s2, 2p6, and the next is 3s, only 1 electron left, so it'll end there here. Or we can simply write, since this is similar to neon, we can also write neon and then 3s1, and the other electron will go here. Now let's talk about argon. So argon has helium, neon, argon. Argon will have 3s2, so 10, 12, I think 16, I think 18. So we can write, since up to neon it'll be same, so neon, and then we can write 3s2 and 3p6. So next up is 3p. Now let's go to calcium. So calcium has 20. Now after filling up this neon, so up to 18 will have argon, but the next electrons, and there's the 4s subshell, 4s2, the next 2 electrons here, 4s2, so that is the, because we have after 3p we have 3d also, but the electrons don't enter 3d, it straight away goes to 4s. That is why this of Paul's rule or is important in filling up of or in writing electronic configuration. We fill the 1s first, then the 2s, then 2p and 3s, then 3p and 4s, then only we go to 3d. Suppose when we talk about scandium, which is 21, the electronic configuration will look like argon, and then the next electron enters 3d first, then 4s. So that is how we write for scandium. Because in calcium we straight away go to 4s, and then but in for calcium, but in scandium we put the extra electron in the 3d orbital, because as you will know in your further chapters, that these these electrons are the ones that gets oxidized before the 3D electrons. So to complete the off-pose diagram, 4s, 4p, and 4d, and then we'll have 4f, 5s, 5p, 5d, 5f, 6s, 6b, 6d, and so on. So we'll feel this way. So always remember this off-pose diagram, so that once this orbital is filled, if there are any remaining electrons, it will go to 2s orbital. Once it is fully filled, it will go to 2p, then 3s, and so on. That is how we feel, or that is how we write the electronic configuration of any particular atom. So there are two more rules for writing the electronic configuration. The first one is our Wolfgang Pauli's exclusion principle. This states that when filling up of electrons in an orbital, each orbital, we know that suppose for s orbital we can have 2 electrons, maximum of 2 electrons, but Pauli's exclusion principle suggests that the 2 electrons cannot have the same spin. It will have opposite spin. If one spin is up, the next electron will have a down spin, so that they neutralize each other and they are stable. And the next rule is our Hund's rule, and this rule suggests that suppose in p orbitals, let's take the example of a p orbital because it has 3 subshells. So if in p orbital there are 3 electrons, then this p orbital will be filled, the 3 electrons will be filled singly first. Then if there are extra electrons, then only pairing of electron will take place. That's our Hund's rule. So those are the 2 rules. So let's try to take an example of say carbon. So carbon has 6 electrons. So in 1s orbital, so the electron configuration will look like 1s2, 2s2, and then 2p. There are 2 electrons gone, so only 2 electrons are left, so 2p2. So the 1s orbital will have 2 electrons of opposite spin, 2s similarly 2 electrons of opposite spin, and in 2p orbital we have 2 electrons, so they'll be first filled simply first, the same spin. Or let's take the example of say sodium. So sodium has 11 electrons, so the electronic configuration would be 1s2, 2s2, 2p6, 10 gone, and 3s1. So the spin will be for 1s, for 2s, for 2p, then pairing will start, that is 6 electrons, and in 3s there will be 1 electron. That is how we write the electronic configuration, different electronic configurations, except for chromium and copper. We follow this same rule. In chromium and copper there is an anomaly. Suppose copper has 29 electrons. So if you write the electronic configuration, 1s2, 2s2, 2p6, 3s2, and then 3d, 9, and 4s2, 10, 3d, has to be 29. Oh, sorry, 3D, 3S, 3P6, then 3S, 3P6, then 3D9 and 4S2, 3D9 and 4S2. So then 29. But this is wrong. We have to write 2S2, 2P6, 3S2, 3P6, 3D10, and then 4S1. One electron is reduced from the 4s orbital and it enters the 3D orbital because it has when 3D10 is when we completely fill the 3D orbital, then it is more stable as compared to this, and chromium electronic configuration or chromium stays in this way. Similarly, chromium also follows this rule. So I hope you have understood something on this electronic configuration. So this is the end. We've come to an end of this chapter. I think I'll be giving you a handout for some handout of some problems so that you can solve it at home.